Hello, and today's purpose of the day is I can solve absolute value inequalities and graph inequalities with two variables. Let's take a look at a couple examples of absolute value inequalities. Absolute value, as a reminder, is the distance away from zero and must always be positive. So I'll fill in here the definition, get my stylus working. Distance away from zero, and it's always positive. The symbol for absolute value is bar notation, so I'll put bars on both sides of the expression that we're working with. And let's review a couple steps of absolute value inequalities. Step one, to set up two inequalities, make sure that the absolute value is first isolated. So when it's isolated, then we'll set up the two inequalities, one that is exactly as you see, and the other one is the sign or the inequality symbol switched, and then the opposite answer on the other side of that inequality. Then the second step would be to solve both inequalities. And then the third step would be to graph. And we'll make sure that with these inequalities, if it's an and statement, that we will write our final answer appropriately. And if it's an or statement, we will write our final answer appropriately as well. So let's take a look here at a few examples. So the absolute value of a minus 5 is less than 3. So here I'll set up the first inequality, that's a minus 5 is less than 3. And then the second inequality is a minus 5 is greater than negative 3, because we know with absolute value that the absolute value of an expression could be negative to begin with, but then when we actually take the absolute value of that, it becomes positive. So we always have to set up two cases. So if I solve this first one, I'll add 5 to both sides and get a is less than 8. Then I'll add 5 to the other side here and get a is greater than 2. So I have a is less than 8 and a is greater than 2. So if I am going to graph this together, I know I need open circles at 2 and 8, just because it's greater than or less than. And then if I want everything less than 8, they'll shade this way, but greater than 2 will shade that way. So this is actually an and statement because I have an overlap. So my final answer would be a is greater than 2, but less than 8. And then that would also be my final graph as well. So this would be my full answer here for the first example. Okay, for the second example, I'll write u plus 3 is less than 7, and the other will be u plus 3 is greater than negative 7. I'll go ahead and solve these two inequalities. Get u is less than 4, and then get u is greater than negative 10. So if I were to graph these, I would have negative 10 here, 4 there, and I want everything less than 4. So I'll shade this way, but then greater than 10. So again, we have an and statement here. So u is less than 10, but u is greater than 4. So that would be my final answer for number 2. Number 3 says the absolute value of t plus 4 is less than or equal to negative 2. Well, before I begin to set up my two inequalities, I need to look at what's on the right side of that inequality symbol, meaning, negative 2. So t plus 4, the absolute value of that must be less than or equal to negative 2. Can the absolute value ever be less than or equal to a negative number? No, it can't. So if ever or whenever you see a negative sign, or a negative number, on the other side of the inequality sign, so essentially any absolute value is less than or equal to a negative number. That's always false, right? That can't happen. So here, this is no solution, and an empty graph would be my solution set because I don't have a solution. All right, number 4, and again, all of these absolute values here that we're starting with are already isolated, but we would need to make sure that our absolute value is isolated before we can begin to set up our two inequalities. So number 4 says the absolute value of c plus 4 is greater than -2. Well, the absolute value of an expression is greater than a negative number. That will always be true. So here, this is another special case. This is all reals, and my graph would all be filled in because every answer would be a possible solution. Now I'm just going to add in an example to the notes. So I'm going to come right back to this, the graph of an inequality portion, and I'm going to just add in an absolute value inequality and just talk about what you would actually do to solve this inequality. So if I had something like this, and if you want to add this to your notes, that would be a good idea. And I apologize that it wasn't in your notes to begin with, but to solve this inequality, we need to first isolate the absolute value. So what I would do here is I would add 3, because I can't write my two statements yet until I've got it completely isolated. It's greater than or equal to 10, and now I would divide by 9 to get rid of that 9. So now I can actually set up my two cases. I would have the absolute value of x minus 5 is greater than or equal to 10/9, and then my second case would be the absolute value of x minus 5 is less than or equal to -10/9. And I won't go ahead and solve that, but I just wanted to show you how you would isolate that absolute value and then write your two cases. Okay, let's go right back up to the beginning of graphing inequalities with two variables. So I'm going to change to a different concept now with still inequalities. But the graph of an inequality with two variables includes all coordinate points that would make the inequality true. Okay, let's take a look at a few examples. Okay, so the boundary line is the plotted line of an inequality. I'm going to zoom in here a little bit. So that's a vocab word. So I would say here, plotted line. And then the half plane is the region of the graph on one side of the boundary. So what this would look like is I'll have my coordinate plane, I'll have my line graphed, and that's my boundary line, and it could be dashed or solid. And then I have two half planes, so I have one over here and I have one over here, and only one of those half planes will be shaded to show the solutions to the inequality. So steps for graphing an inequality, just to remind ourselves. We'll want to change to slope-intercept form, and slope-intercept form again is y equals mx plus b. Great job for knowing that. If necessary, it might already be in slope-intercept form, then we wouldn't have to change it at all. Number 2, graph the y-intercept and move according to the slope. For less than or greater than, use a dashed line. And for less than or equal to or greater than or equal to, we will use a solid line. We'll test a point in one of the half planes, and the easiest point to plug in is 0, 0. But if that point is on the line, we can't use that point. We'll have to use something else like 0, 1, 1, 0, other numbers that would be easy to plug into our equation to see which half plane would be the solution. And then we'll shade the half plane that makes the inequality true. Inequality or the equation true. Okay, so let's continue on. So if we take a look at a few examples here, again, we want to get these into y equals mx plus b if they're not already in that form. And so what I'll do here is I'll go ahead and graph y equals 2x minus 1, and I'll just zoom in on one example first. And I'll plot my y-intercept, go down 1, and then I'll move according to my slope, so up 2 units, over 1, or down 2 units to the left 1. And this is a solid line because it's less than or equal to. And if I test the point 0, 0, is 0 greater than or equal to 2 times 0 minus 1? Well, 2 times 0 is 0, so is 0 greater than or equal to negative 1? It is, so where 0, 0 is right there, we will shade that half plane. And that will be the solution to that inequality. Now I'll jump down here to this example, because this example is actually not in slope-intercept form, so we have to rewrite it first before we can attempt to graph. So I'll subtract 2x and get y is less than negative 2x plus 3. And now that's in slope-intercept form. So what I'll go ahead and do is I'll graph the y-intercept, and this should be actually minus 3, right? 2x minus, negative 2x minus 3. And I'll go down 3 on the y-intercept, and then down 2 over 1, or the up 2 to the left 1. And this is a less than symbol, so I need to do a dashed line. And then I'll plug in the point 0, 0, so I could say 0 less than negative 2 times 0 minus 3. Well, negative 2 times 0 is 0 less than negative 3? No, it's not, so where 0, 0 is, I shade the other half. So the other half would be the solution here to this inequality. Feel free to go through a few more examples and do the other two on the video, or the other two on your notes, and I'll post the answers in the video in a moment. All right, please feel free to check your answers for those last two examples. Thanks for listening. Have a great day. Bye-bye.